Example 11.2. In this example, a long cylinder of radius of 0.8 meters is hinged at point A and is used as an automatic gate, as is shown in the picture. When the water level reaches 5 meters, the gate opens by turning about the hinge at point A. We need to determine the hydrostatic force acting on the cylinder and its line of action when the gate opens. We also need to determine the weight of the cylinder per meter length of the cylinder. For us to analyze this problem, we're going to neglect the friction effect on the hinge, and we're going to assume the atmospheric pressure is acting on both sides of the gate. Let's start with a free body diagram. We're going to start doing the forces acting on this section of the water, which is the one in contact with the cylinder. We're going to have a pressure distribution on this section, therefore that is going to create a force that is going to be horizontal, and we're going to call it Fx. The vertical component, this part of the water, is going to create also a force, and we're going to call it simply Fy. And then this water has a particular weight, so we're just going to call it the weight of the water. The cylinder is going to have a reaction force, which is going to be basically the opposite of the reaction. It's going to go in the opposite direction, and it's going to have two components. One that is going to be the vertical component and the horizontal component. And these are the values that we want to find out so that we could get the reaction force. Notice that for this body diagram, the value of the horizontal force Fx is equal to the Fh, which is the reaction force in the horizontal direction. So Fx is going to be equal to Fh, and Fx is simply going to be equal to the multiplication of the average pressure applied into this section times the area that we're going to have. To calculate the average pressure, we simply multiply rho, g, and hc, and we multiply it by the area. For us to calculate the value of hc, notice that we're simply going to take this as a rectangular section. So if we draw this from the side, this is the area of the water that in which Fx is being acted upon. So it's going to be a rectangular section. Therefore, middle of it is where the location with the centroid is going to be, and the height from here to here is equal to 0.4. And from the top, we notice that from here to here is going to be 4.2. So 4.2 plus 0.4 is going to be equal to 4.6 meters. Once we have that, we notice that the area acting upon, so this pressure is acting upon, once again, this cross-sectional area, and that is simply going to be equal to 0.8 meters, and we're going to take it to be 1 unit length in depth. So if we put all these values over here, we find that the value of Fx is going to be equal to 1,000 kilogram per meter cubed times 9.81 meter per second square times 4.6 meters times 0.8 meter square, and that gives us a horizontal force equal to 36.1 kilonewtons. To calculate the vertical component of this reaction force, we simply said that that is going to be equal to Fy minus the weight of the water. For us to calculate the value of Fy, we simply take the value of the pressure average at that point times the cross-sectional area. Notice that Fy is applied at the bottom, so it's basically like taking this cross-sectional area, and then Fy is being applied in that particular point. The amount of the pressure at that point is all the way at the bottom. Therefore, is going to be rho G, and this elevation at the bottom times the cross-sectional area. Therefore, the values are going to be 1,000 kilograms per meter cubed, 9.81 meter per second square, H, which is the value from the surface of the water to the location at the bottom, which is equal to 5 meters, and the area is going to be equal to 0.8, which is the radius of the circle, which corresponds to this section over here, times the depth, which is, we take it to be 1 meter. Therefore, the value of Fy is simply going to be 39.2 kilonewtons. To calculate the weight of the water, we simply take the mass times gravity. We do not know the mass, but we could calculate the volume using density times volume, and once again by gravity. To calculate the volume, we could simply see that this is a square minus a quarter of a circle. So the volume is going to be r squared, that is the area of the rectangle or the square, minus a quarter of a circle, so it's going to be pi r squared divided by 4. So that's the total volume that we have. And we do once again 1,000 kilograms per meter cubed times the volume, and that is going to be equal to 0.8 meters square minus, so we take this out and we do 0.8 meter square times pi divided by 4, and that's your volume, times 9.81 meter per second square. And that tells us that the value of the weight is equal to 1,347.35 newtons. If we take these two values of Fy and the weight, we could calculate that the vertical force is going to be equal to 37.9 kilonewtons. Now that we have two components of the reaction force, Fh and Fv, we are able to calculate the total reaction force, which is going to be Fr. We use Pythagorean theorem, and we simply said Fh squared plus Fy squared. We substitute these two values and we take the square root, and we find that the value of the reaction force is equal to 52.3 kilonewtons. To find that the line of action, we're going to calculate the angle, and the angle is simply going to be inverse tangent of F vertical divided by F horizontal. If we do this calculation, we can find that the angle is going to be around 46.4 degrees. Let's now go to part B, in which we need to calculate the weight of the cylinder. The way that we're going to do it is by analyzing the system when the gate is opening. It's right about opening. Therefore, we're going to neglect the force of the reaction force at the bottom. And the two forces that are acting on the cylinder are going to be simply the weight of the cylinder and the reaction force. To find this weight of the cylinder, we're going to evaluate the moments that these two forces have about point A. So we're going to do the summation of the moments about A, and that is going to give us the weight of the cylinder has an arm of R from point A, and this is going to be negative since it's clockwise, and then the component of FR, which is going to be vertical, is going to be FR times sine of the angle, and has a moment of R. And this summation of moment has to be equal to 0. Therefore, we could calculate that the weight of the cylinder is going to be simply FR times sine of the angle. And then we simply take that to be 52.3 kilonewtons times sine of the angle that we obtained on the previous step, 46.4 degrees, and that gives us a weight of 37.9 kilonewtons. Please go back and double check all the calculations and make sure why we're doing different moments or why we're using different forces in order to obtain the results in this problem.